You know that feeling when you're staring at a time and work problem on a test and your brain just starts to short circuit? Yeah, you're not alone. These questions have a reputation for being super tricky, but today we're going to pull back the curtain and show you how to solve them easy.
So, take a look at this classic example. You've got different people working at different speeds, people working for a few days, and then you have to figure out a fraction of what's left. It's a lot to juggle, and honestly, it looks pretty intimidating. Where do you even begin with something like this?
Well, the old school wave throws you right into the deep end with fractions. You know, person A does 1/15th of the job per day, person B does 1/20th, and suddenly you're trying to find common denominators and your paper is just a mess of numbers. It works, I guess, but it's slow and man, is it easy to make one tiny mistake that throws the whole thing off.
But what if I told you there's a way to solve these problems, even the really complicated ones, without ever having to deal with those messy fractions? A method that's way faster, way more intuitive, and frankly, a lot more fun.
It's called the LCM method, and trust me, this is the secret weapon you need to turn these confusing puzzles into simple, straightforward arithmetic.
The whole strategy is built on this one simple, powerful question. Instead of thinking in abstract bits and pieces of a job, we're going to create a concrete, measurable amount of work using numbers that are actually easy to work with.
So the first big idea is what we call total work. We basically invent a total number of units for the job. And how do we pick that number? Simple. We find the least common multiple, the LCM, of the days each person takes. This one move, right at the beginning, is what vaporizes all the fractions.
The second key idea is efficiency. Now, this is just a fancy word for speed. Think of it like miles per hour, but for work. If the total job is, say, 60 units, and it takes someone 10 days, their efficiency is just 6 units per day. It's a super simple calculation that gives us a clear number for how fast everyone is working.
So how does this all come together? Well, it's this simple, 3-step recipe. First, you define the total work using the LCM. Second, you calculate the efficiency, or speed, for everybody involved. And third, you just use those clean, whole numbers to solve the puzzle. All right, enough theory, let's actually put this thing into practice.
We're going to start with a nice, straightforward example just to get a feel for how slick this really is.
Here's our problem. We've got Amit, who can do a job in 10 days, and Vineet, who takes 15 days. The question is, if they team up, how long will it take them to get it done?
Okay, step 1. We need our total work. So what's the least common multiple of 10 and 15? It's 60. So from now on, this job isn't just a task. It's a project made of exactly 60 units. This is the magic number.
Now for step 2, let's figure out their speeds. Check out the table. For Amit, we take the 60 total units and divide by his 10 days. That gives him an efficiency of 6 units per day. For Vineet, it's 60 divided by his 15 days, which is 4 units per day. See that? No fractions in sight, just nice, clean work rates.
And now we solve. It's the easy part. When they work together, you just add their speeds. So 6 units plus 4 units gives us a combined efficiency of 10 units per day. To finish a 60-unit job at that rate, it's just 60 divided by 10. And that gives us exactly 6 days. Simple, clean, and done.
Okay, that was the warm-up. But the real beauty of the LCM method is how it handles the truly messy problems, the ones where people are coming and going from the job.
So let's level up and tackle this beast. We've got 3 people, all with different speeds. 2 of them start the job, work for a few days, and then, poof, they're gone. Then the last person has to come in and finish whatever is left. This is exactly where the old fraction method would turn into a total nightmare.
Now, to track everything that's happening, we can use a formula that you definitely already know. Speed times time equals distance. Well, the logic here is exactly the same. As you can see, efficiency, which is our speed, multiplied by time equals the amount of work done. This simple idea is how we're going to keep everything organized.
So, let's get this set up. Same playbook as before. Step 1. Find the LCM of 24, 9, and 12. That number is 72. So our total work is 72 units. Step 2. Calculate efficiencies. A's is 3 units per day, B's is 8, and C's is 6. Okay, now we start tracking the action. B and C start the job together, so we add their speeds. 8 plus 6 equals a combined efficiency of 14 units per day.
The problem says they work for 3 days. So we use our formula. 14 units a day times 3 days means they completed 42 units of work. So what's left to do? The total job was 72 units. They already knocked out 42 of them. A simple subtraction tells us there are 30 units of work remaining. Now A has to finish this all by himself. We know A's efficiency is 3 units per day. So 30 divided by 3 tells us it will take A exactly 10 more days to finish the job. See? No sweat.
So there you have it. We've seen this method crush both a simple problem and a really tricky one. Let's just boil this all down into a reliable framework that you can use every single time you see one of these questions.
Here's your game plan in 4 simple steps. 1. Define the task by finding the LCM. 2. Calculate the speed or efficiency of each worker. 3. Track progress by multiplying that speed and the time they worked. And 4. Solve by simply adding or subtracting the units of work. Follow these steps and you'll nail it every time.
And that's really the cool part, right? We took a problem that looked like a complete mess of fractions and transformed it into a series of simple, logical steps. It kind of makes you wonder, what other complicated problems out there are actually simple if only we can find the right framework to look at them? Thanks for watching.